Hello students, welcome to our student support program grade 11 additional mathematics. Today we are going to use integration to evaluate area under the curve. So let's begin. Area under a curve. An important application of integration is in finding the area under a given curve y is equal to f of x. Up to now, areas could only be found approximately, for example, by counting squares. Using calculus, we can now find the exact value of areas bounded by curves. This figure shows part of the curve y is equal to f of x. The shaded area A lies between the curve and the x-axis, bounded by the ordinates at A and B. This area is called area under curve between A and B. This area is calculated by the definite integral of the function f of x from A to B. The definite integral of a function gives us the shaded area between the curve, the x-axis, within the specific bounds. It is denoted as the area is equal to the integration of f of x with respect to x between A and B, where f of x is greater or equal to 0. Let's apply this rule to some examples. Example 1. Find the area of a shaded region. Area under the curve between 2 and 3 is written as follows. The integration of x to the power of 3 with respect to x between 2 and 3. First, we are going to integrate the function to obtain x to the power of 4 over 4 between 2 and 3. Substituting the limits now, we get 3 to the power of 4 over 4 minus 2 to the power of 4 over 4, which is equal to 81 over 4 minus 16 over 4. Evaluating this, we get 16 1/4 units square. Now let's have a look at area below the x-axis. If the required region between y is equal to f of x and the x-axis lies below the x-axis, the definite integral will be negative. Hence, for a region that lies below the x-axis, the area is given as follows. Area is equal to modulus of integration of f of x with respect to x between the limits A and B. Let's apply this rule to example 2. Find the area of a shaded region. First, we are going to calculate where the curve crosses the x-axis. Factorizing the x squared minus 5x plus 6 is equal to 0, we get x minus 2 into x minus 3 is equal to 0. X is equal to 2 and 3. Now the shaded area will be the modulus of integration of x squared minus 5x plus 6 with respect to x between the limits 2 and 3. Integrating the function, we get x to the power of 3 over 3 minus 5x to the power of 2 over 2 plus 6x between the limits 2 and 3. Substituting the limits, we get 3 to the power of 3 over 3 minus 3 to the power of 2 over 2 plus 6 multiplied by 3 minus 2 to the power of 3 over 3 minus 5 multiplied by 2 to the power of 2 over 2 plus 6 multiplied by 2. Evaluating this, we get 1 over 6 units square. Example 3. Find the area of a shaded region. The required region consists of a section above the x-axis and a section below the x-axis. To evaluate this area, we need to consider each section separately. The area of a shaded region will be as follows. The integration of 2 sine x with respect to x from pi by 3 to pi plus modulus of integration of 2 sine x dx between the limits pi to 3 pi by 2. Integrating the functions, we get minus 2 cos of x over 1, where 1 is the derivative of the angle, between the limits pi by 3 to pi, plus modulus of minus 2 cos of x over 1, where again 1 is the derivative of the angle, between the limits pi and 3 pi by 2. Now we shall substitute the limits. Minus 2 cos pi minus 2 cos pi by 3 plus modulus of minus 2 cos 3 pi by 2 minus 2 cos of pi to get 2 minus 1 plus modulus of 0 minus 2. Evaluating this, we get 5 units square. Please note that area is a scalar quantity that is always positive, and when working with trigonometry ratios, your calculator should be set on radian mode. Now that we have done some examples, here are some exercises for you to practice. So students, today you have learned how to use integration to evaluate area under the curve. I hope you have enjoyed it. See you next time.